We are continuing our survey of intermolecular forces from the strongest to the weakest. When we had fully charged ions, we called the intermolecular force ion-ion interactions, or ionic bonds. When we had an ion attracting a polar molecule, that was called ion-dipole interactions. When we had two polar molecules, we called it a dipole-dipole interaction, and we looked at the special case of hydrogen bonds. But now we're going to continue looking at the attraction between a polar molecule and a nonpolar molecule. And I'm going to have to explain for you why a nonpolar molecule is referred to as an induced dipole in the title. So you remember that everything is held together by attractions between opposite charges. And here comes my water molecule approaching an oxygen molecule that must be nonpolar. The two oxygen atoms must have the same electronegativities. That's not a polar bond. So how could something with a partial charge attract something with no charge? Well, it's not that there's no charge in the oxygen. Within the O2 molecule, there are lots of electrons moving around. And when the negative end of the water molecule comes up to it, it repels the electrons in the oxygen just a little bit. And that makes the far end of the oxygen molecule just a little bit negative. I put two deltas there, little bit. And that leaves this side a little bit positive. Now that I have opposite charges next to each other, they can attract. And that makes the ion-induced dipole force. The polar molecule, the dipole, the water in this example, induced a dipole, or made the O2 polar, even though it wasn't polar in its own right. Now this is a pretty weak force, right? That's a tiny charge separation that we see in the O2 molecule. It's a very weak intermolecular force. Oxygen isn't very soluble in water, but fortunately for the fish, it is somewhat soluble, or the fish would die. Last and weakest kind of intermolecular force. Induced dipole interactions, and those are attractions between one nonpolar molecule and another nonpolar molecule. Now, these are called induced dipole interactions. They're also called London forces, or dispersion forces, or London dispersion forces. You may have heard of them in biology class, and I don't care which name you have for them. I'm used to seeing them by all of those names. Now, this is the attraction between two nonpolar molecules with uniform charge distributions. If there's no charge, how can they attract? Well, here's the rationale. What they say is that due to the random motion of electrons, temporarily the molecule becomes polar for a split second. The electrons just happen to be a little closer to this end 1 second than to this end. If you look the next split second later, those electrons have moved again, and those tiny dipoles have been moved to another part. In a time averaged way, the molecule isn't polar overall, but at any split second, you can get a temporary misalignment of electrons, you get a temporary dipole. When that happens in one molecule, it repels the electrons in the other molecule, leaving this end a little bit positive. And I'm going to say a little bit, like I did on the previous slide. So now we got a little bit negative attracting a little bit positive, and that's what holds nonpolar molecules together. Nonpolar molecules do hold together, right? Gasoline that you pump into your car is a liquid. Something's holding them together so they don't fly off into the gas phase. When we looked at the other intermolecular forces, we saw that within the category there were a range of strengths of that force. There's a range of strengths of dispersion forces, and let's see how that goes. Here's some evidence. Liquid nitrogen exists at a very low temperature, almost negative 200 degrees Celsius. And some of you may have had that used to burn off a wart in the doctor's office, maybe. Its boiling point is really, really low because it doesn't take much energy to overcome the attractions between those non-polar nitrogen molecules. In contrast, though, in experiment 2, you worked with solid iodine. That's a solid at room temperature. So the intermolecular forces, the dispersion forces in I2, must be stronger than the dispersion forces in N2 to hold it in a solid to such a high temperature. You will notice, though, that the forces are weak even in iodine. If we put a lid on it, the iodine will actually sublime and crystallize on the underside of the watch glass. Pretty cool. So why are the dispersion forces in iodine stronger? The strength of the induced dipole, or dispersion forces increases with not polarity, but polarizability. Remember, we have to make these temporary dipoles to distort the electron cloud just a little bit so that one end has a bit more electron density and the other side has a little bit less. I can polarize it, I can make it polar more easily if I have more electrons to work with. And if those electrons aren't tightly held by the nucleus, say in the higher energy levels, they can move around more freely. To put those two things together, if I have more electrons in a molecule that has higher molar mass, I'm going to have stronger dispersion forces. So continuing on this trend, here are all the halogens. Fluorine is a gas at room temperature. Chlorine is a gas. Bromine is one of 2 liquid elements, although you can see it's pretty volatile. In the sealed flask, it puts a lot in the vapor phase. And iodine is a solid. I hope that trend makes sense. As those molecules get bigger and bigger, with more and more electrons, and the valence electrons in higher energy levels further from the pull of the nucleus, they can be moved around more easily. The molecule is more polarizable. I couldn't predict which one would be the gas, which would be the liquid, and which would be the solid, but I do know that as I go down the group, it makes sense that it goes from gas to liquid to solid. One last thought about dispersion forces. Because they're due to the random motions of electrons, and everything has electrons, there are dispersion forces involved in all compounds to some extent. Often, when we look at a substance, there'll be more than one type of intermolecular force involved. But because dispersion forces tend to be so weak, I am going to focus on the dominant intermolecular force when we solve our problems together. All right, here's a little summary. From the strongest to the weakest, we can have attraction between fully charged ions, an ion-ion interaction, or an ionic bond. I can have an ion attracting a polar molecule. That's an ion-dipole interaction. I can have a polar molecule attracting another polar molecule. And there's a especially strong case called hydrogen bonding that I'll actually move up in the order like that. Dipole-induced dipole is a non-polar molecule with a polar molecule. And finally, induced dipole, which I usually call dispersion forces, is attraction between 2 nonpolar molecules. And so you don't have to memorize which is stronger. Just look at the particles and see how big the charge is. Good old Coulomb's law. So let's finish up by doing some practice together. The question here is, what is the dominant intermolecular force between molecules of the following thing. Let me model the questions I would ask myself to solve this problem. Because the intermolecular force depends on whether I have fully charged particles or charged particles, the first question I'm going to ask myself is it ionic or is it covalent? Now, the first example has only nonmetals. It's covalent. Be careful, that's different from NH4OH, which would be ionic with an ammonium ion in it. Okay, so I know it's covalent. Next question I'm going to ask myself is it polar or not? Well, it's way polar. Actually, I've got hydrogens bonded to oxygens and hydrogens bonded to nitrogens. So I can see that this is capable of hydrogen bonding. And remember, that means not that there's a bond to hydrogen within the molecule, but that there's a strong attraction to another molecule. That's the hydrogen bond. Okay, next example, OF2. First question I'm going to ask myself is it ionic or covalent? It's covalent. All right, so covalent things can have either be polar or nonpolar. So the next question I'm going to ask myself is it polar or nonpolar? This one's going to take a little bit more work. To know if a molecule is polar or nonpolar, first I need the Lewis structure to tell me the shape. This one is bent, so that I can see if the bond dipoles cancel out. Because it's bent, it's polar, and therefore the dominant intermolecular force is dipole-dipole. All right, you've seen me think through a couple. Next one we're going to look at is sodium nitrate. Pause the video and decide what the dominant intermolecular force is. I see metal and non-metal. I see an ionic compound. So this is quick to do. If I've got two ions, I've got an ion-ion interaction. Or an ionic bond. That's equivalent. Last example. Pause the video. See what you can do. All right, first question. Is it ionic or covalent? It's covalent. Next question. Is it polar or nonpolar? Well, it's got to be nonpolar. There's no polar bonds in it. All the atoms are the same and have the same electronegativity. So if it's nonpolar, the intermolecular force is the very weak dispersion force, or induced dipole, induced dipole. All of these other examples have some attraction due to random motion of electrons. All these other examples have dispersion forces involved as well, but I asked for the dominant intermolecular force. So just for fun, which one do you think would have the highest melting point? The one with the strongest intermolecular forces, right? More energy to pull the ions apart so it can flow as a liquid. And the lowest melting point would be the one with the weakest intermolecular force. All right, friends, that is my story for Chem 110, Chem 122. But that is not the end of my commitment to you. I will see you in Zoom class and in office hours whenever you need me. Stay in touch.